Hello everyone. In this session, we will going to solve 3 more problems on lumped heat analysis. Now coming to overview of this session, first we will glance all the formulae which are required to solve the problems. Then we will solve 3 problems on lumped system analysis. Now coming to characteristic length, it is the ratio of volume of the solid to the surface area of the solid. LC characteristic length for different geometric shapes as below. For flat plate, LC is thickness by 2. For cylinder, it is R by 2. R is the radius of the cylinder. For sphere, LC value becomes R by 3. For cube, LC value becomes L by 6. Now, Biot number, that is the ratio of internal conductive resistance to the external conductive resistance, HLC by K. H is the convective heat transfer coefficient, LC is the characteristic length, K is thermal conductivity. Next, Fourier number, that is alpha T by LC square. Alpha is thermal diffusivity, K by rho C. Now, notations for lumped heat analysis. Different textbook will use different notations. Okay. Now we will solve third problem. 2 problems already solved in the last session. Now coming to third example. An average convective heat transfer coefficient for flow of 90 degrees Celsius air over a flat plate is measured by observing the temperature, time history of a 40 mm thick copper slab, density 9000 kg per meter cube, specific heat 0.38 kilojoule per kg Celsius, then thermal conductivity 370 watt per meter degree Celsius exposed to 90 degree Celsius air. In one test run, the initial temperature of the plate was 200 degrees Celsius and in 4.5 minutes the temperature decreased by 35 degree Celsius. Find the heat transfer coefficient for this case. Neglect internal thermal resistance. Neglect internal thermal resistance means we have to use lumped system analysis. Now if you see the problem statement, ambient temperature, that is exposed to the air, that is atmospheric temperature. Atmospheric temperature here 90 degrees Celsius, this environment 90 degrees Celsius. Then thickness given 40 mm, that is converted into 0.04 meter, density given, Cp value given. Then initial temperature is given 200 degrees Celsius. Then 4.5 minutes given. After some time interval t, 4.5 minutes, that you have to convert it into second, that is 270 seconds. Then the temperature is decreased by 35 degrees Celsius. Initial temperature was 200 and after some interval time t, that is 4.5 minutes, the temperature is decreased by 35 degrees Celsius. Then T value after the time 4.5 minutes 165 degrees Celsius. Subtract 35 from 200. We have to find out convective heat transfer coefficient. For that, first you have to find out LC, V by AS, because here there is no information about the length, breadth, height, but thickness they have given directly. For flat plate, LC characteristic length is nothing but L by 2. This L value given in the problem, so just substitute and get the value of LC, that is 0.02 meter. Temperature distribution equation for lumped heat analysis, here directly it is not possible to find Biot number. because for lumped system analysis Biot number should be less than 0.1, but in the problem it is given that neglect internal thermal resistance. That means we can use this temperature distribution equation from lumped heat analysis. We have to find out H. Remaining all the values we have, just to substitute T value we have, TA value we have, TI value we have, then e power AS by V is nothing but it is 1 by LC. You see the V by AS is LC. AS by V is, it is 1 by LC value, we have LC, and time T also we have. Rho value we have, then specific heat C value we have. Only H is the unknown. So this value they are finding first, HAS divided by rho into V into C. H divided by, just they have substituted A, V by A goes to the denominator, that is V by A into C, that is nothing but H into rho into C, this V by A is LC. So they have written whole term in terms of H now. Now you see, after substitution 165 minus 90 divided by 200 minus 90 e power, that whole term they have written here in terms of H. Okay. Now 0.682 equal to 1 by e power of 0.003947 into H, that is nothing but e power of 0.003947 equal to 1.466. This H we have to find out. Take ln both sides. So this side becomes 0.003947 H is equal to ln of 1.466. Finally, if you simplify this equation, you will get H as 96.9 watt per meter square degree Celsius. Now going to the fourth problem. The heat transfer coefficients for the flow of air at 28 degree Celsius over a 12.5 mm diameter sphere are measured by observing the temperature time history of a copper ball of the same dimension. The temperature of the copper ball was measured by two thermocouples, one located in the center and other near the surface. Both thermocouples registered the same temperature at a given instant. In one test, the initial temperature of the ball was 65 degrees Celsius, and in 1.15 minutes, the temperature decreased by 11 degrees Celsius. Calculate the heat transfer coefficient for this case. Again, Cp value given, K value and Cp value and rho density value given in this problem. Then heat transfer coefficient of the air we have to find out here. Air at 28 degrees Celsius means it is an environment now. Environment temperature 28 degrees Celsius, that is TA. Then R value, it is for the sphere, it is a sphere. So LC value nothing but R by 2. Okay, that is 0.00625 meter. C value given 0.4 kilojoule per kg degree Celsius. Then density value given, Ti value given, then temperature T indirectly given. See here, after some interval of time T, that is 1.15 minutes, temperature is decreased by 11 degrees Celsius. It is similar to last problem. 65 is the initial temperature, TA value, sorry, TA value is ambient temperature, Ti value is the initial temperature 65 degrees Celsius. Okay, this 65 degrees Celsius after 1.15 minutes it is decreased by 11 degrees Celsius, that is 65 minus 11 equal to 54 degree Celsius. Time is given 1.15 minutes, that is 69 seconds. We have to find out H value. Since the heat transfer coefficient has to be calculated, so assuming that internal resistance is negligible and Biot number is less than 0.1. In this problem, no information about the internal resistance, whether we have to neglect or not, but you have to assume internal resistance is neglected and Biot number is less than 0.1, then only we can go for lumped capacitance method. Then remaining temperature distribution equation is same, T minus TA divided by Ti minus Ta is equal to e power of minus h into area divided by rho into V into C into time t. Only unknown is h. Just to simplify, h is equal to, from this equation, in this step itself they have taken ln in order to remove this e power. So if you take ln both sides here, ln of T minus Ta divided by Ti minus Ta is equal to, exponential will go when you take ln this side, this remaining is minus h into area into divided by rho into V into C into time, that is written here. Then we need h value because we have to find out convective heat transfer coefficient, that h is equal to, from this equation, rho into V into C divided by As into time into ln of this term. So if you simplify this term, V by A, V is the volume of the sphere, 4 by 3 r cube, pi r cube divided by area, surface area of the sphere is 4 pi r square. You can directly write because it's a LC value, LC for characteristic length for sphere is r by 3. This value we already know. For the LC for the different geometric shapes already we have discussed. So remaining term just as it is you write, and except h value, all values we have just substitute and get the solution for h. Finally you will get, if you substitute all the values in the equation, in this equation you will get 37.71 watt per meter square Kelvin. Now going to example 5. A steel ball 50 mm in diameter and at 900 degrees Celsius is placed in still atmosphere of 30 degrees Celsius. Calculate the initial rate of cooling of the ball in Celsius per minute. Take density 7800 kg per meter cube. C means specific heat 2 kilojoule per kg degree Celsius for steel, and convective heat transfer coefficient H value as 30 watt per meter square degree Celsius. Neglect internal thermal resistance. Please observe this sentence. Neglect internal thermal resistance means we can use lumped system analysis. The meaning of this is Biot number is less than 0.1, we can use lumped system analysis. Here we have to find out rate of cooling of the ball in Celsius per minute. So R value 50 by R value is diameter by 2, that is given 25 mm, 50 by 2, that is 0.025 meter. Then initial temperature is how much? 900 degrees Celsius. It is placed in an atmosphere of 30, so ambient TA 30 degrees Celsius. Density is given, Cp value given, H value given. Time t is 1 minute. Please remember you have to convert minute into second. So temperature variation in the ball with respect to time, neglecting internal thermal resistance, is given by, so this temperature distribution equation by lumped system analysis. So we have to find out rate of cooling. For that you find out after the 1 minute of time what is the temperature change. First you find out temperature using this equation. So first they are finding H into AS divided by rho into V into C into time. This factor first they are going to find. This value is, just you substitute all the values you will get 0.01385. Now we have the value of this H into AS divided by rho into V into C into time. This whole value we have, that is 0.01385. Now you substitute T minus 30 because after the time interval temperature is T. This value we don't have. First you find out T minus 30 divided by 900 minus 30 is equal to e power of minus 0.01385. That is equal to, if you simplify this equation, you will get 0.0 9.9862 as this value. Now T is equal to 30 plus 0.9862 into 900 minus 30 is equal to 888 degrees Celsius. 888 degrees Celsius. Now what is the rate of cooling? Initially the temperature was 900. Now it is reduced to 888 degrees Celsius. Rate of cooling is 900 minus 888 is equal to 12 degrees Celsius per minute, because after 1 minute time the temperature is reduced to 888 degrees Celsius. So initial temperature was 900. 900 minus 888 is equal to 12 degrees Celsius per minute is the rate of cooling. With this, I am concluding this session. The equations for the lumped heat system will be available in your data handbook, Transient Conduction, page number 66. The following references are used for the preparation of these slides. Thank you.